But the only thing I haven't spoken about much yet is the geometry of the complex plane. So sometimes you're solving questions where you have to visualize, complex numbers on the plane. We've spoken a little bit about that, but now I just want to do some more concrete examples. So the first example, start off with an easy one. It says, sketch the set of points in the complex plane corresponding to a modulus of z equals 3. So you want to draw all the points in the complex plane that have a modulus of 3. So remember, modulus means distance from the origin. So if your distance from the origin is equal to 3, then it means you lie on the circle of radius 3. That's really all that it is. So this is let's say this is a circle of radius 3. So I realize that does not look like a circle, I apologize. But using your imagination, right? Let's say this is 3 and this is 3. Real axis, imaginary axis. That would be the answer, right? Because if you take any point on that circle, any complex number on that circle, then its modulus would be 3. Now with questions like this, if you don't see it straight away, that's no reason to panic or to give up, because you can also solve it algebraically. So what I mean by that, let's say I didn't realize that this is a circle. So I could say, okay, we want mod z to be 3, let z to be a random number, call it x plus iy, right? Now we know the modulus of x plus iy is just the square root of x squared plus y squared. And now if I square both sides, I get x squared plus y squared equals 9. And this is the equation of this circle. So you can also solve it algebraically, right? But now that you've seen that problem, it'll probably be easy if you see it in the future. You should recognize straight away that's a circle. Like in this one here, right? I want modulus of z plus 3 to be less than or equal to 2. So think about it. I can think of this as being modulus of z minus 3 is less than or equal to 2. So remember what we said before. In one of the examples that we did, we said if you have the modulus of z minus w, that means the distance from z to w. So this is just another way of saying that the distance from z to the point negative 3 is at most 2. So if you had modulus of z plus 3 equals 2, right? So let's say minus 3 is here. Again, this is the real and this is the imaginary. Actually, maybe I shouldn't put minus 3 here because it might not fit on my page. So let's say minus 3 is here, right? So the distance to minus 3 is at most 2. If the distance to minus 3 was exactly 2, then you'd get a circle again, right? This is if the distance to minus 3 was exactly 2. So you get a circle of radius 2 centered at minus 3. So this would be minus 1, and this guy here would be minus 5, right? But it says that the distance is at most 2. So the idea is it could be anything inside the circle. That's pretty much the idea. So that's why that point that we mentioned before was so important. To remember that if you have the modulus of z minus something, it means the distance from z to that point. So that's the idea of that. So moving on to the next example, we want to sketch the set of points where the principal argument lies between pi on 3 and 2 pi on 3. So if you have an angle of pi on 3, let's say this is pi on 3, right? If you have a principal argument of 2 pi on 3, it's here. The idea is that they're symmetric, right? Because this is 2 pi on 3, this is pi on 3 as well. So if the principal argument of z goes between pi on 3 and 2 pi on 3, it means that you're any point in this region, right? Because if you're any point in this region, your angle is more than pi on 3, but at the same time less than 2 pi on 3. Because this line represents when the argument is 2 pi on 3, and this is pi on 3. Now the reason I've used dotted lines is because it's strictly less than. So in maths, when you draw something using dotted lines, it means exclusive. It means that that line is not included. That's why in the previous example I used it using full lines, because I wanted to include the edge as well. But that one's a pretty straightforward example. Okay, let's have a look at another one. So, sketch the set of points in the complex plane corresponding to z plus 1 equals z plus I. Again, the idea is to use what we spoke about before. If I write this as z minus minus 1 equals z minus minus I, then this is saying that the distance of z from the point minus 1 is the same as the distance of z from the point minus I. Now, if I draw my complex plane, right? So let's say minus 1 is here and minus I is here. I want points that are equidistant from those 2 points. So it makes sense that I need to draw a straight line. Right? Because if you think about any point on this line, it's going to be the same distance apart from minus 1 and minus I, and that's all I want. So that would be the answer in this case. But again, let's say I couldn't see that, right? Sometimes you draw a mental blank. Okay? I could just do it algebraically. I don't have to give up. So I'd say, okay, let's z to be x plus iy. So this becomes x plus iy plus 1 equals x plus iy plus I. So I can write this as modulus of x plus 1 plus iy equals modulus of x plus I times y plus 1. Now the modulus of the left, so this would be square root x plus 1 squared plus y squared, just using the definition. This would be square root x squared plus y plus 1 squared, squaring both sides. I should have probably squared both sides from the start to avoid the square roots. But anyway, you get this. Now if you expand out, a lot of things cancel. In fact, if you expand, the only thing that will remain is 2x equals 2y. Or in other words, y equals x, which is in fact the equation of this line. So you can see that you can also solve it algebraically, right? But intuitively we can see why that's the case. Okay, so the final example that I'll show you is this one. So I want to find all the points that satisfy this relationship here. So this one, not so obvious, right? Unless, of course, you already know, if you're familiar with the shape that I'm going to draw, but otherwise it's not so obvious. So the way to approach this one is to do it algebraically. So like before, what I do is I just let z to be x plus iy, and I just do some algebra to get a relationship between x and y. So if I let z to be x plus iy, then I'm going to get x minus 3 plus iy equals x plus 3 plus iy. Oops, sorry, where did I write equals? I meant plus. Sorry about that. So this should equal 10. Now using the definition of modulus, this is the same as saying x minus 3 squared plus y squared plus x plus 3 squared plus y squared. And that should equal 10. So now taking one of the square roots to the other side, I get that x minus 3 squared plus y squared equals 10 minus square root x plus 3 squared plus y squared. And now I square both sides. I don't know why I forgot the square root here, sorry about that. But now I square both sides, so therefore what I get, the square root on the left disappears. And if I square the right hand side, so I have to use that formula, a minus b squared is a squared minus 2ab plus b squared. So if I use that, then what I get on the left, on the right, sorry, I get 100 minus 20 square root x plus 3 squared plus y squared plus square root disappears now, this one. And so therefore, so a lot of things are going to cancel actually. So the x squareds are going to cancel, the y squareds, the 9, so all that's going to be left is just this. So we're just going to have, just going to get, I think, 100 plus 12x. Yeah. And now what I do is I divide by 4 to make this a bit simpler. So I get 25 plus 3x. And now again, squaring one more time, the last time. So squaring both sides, I get 25 x plus 3 squared plus 25y squared. If I square the right hand side, I get 625 plus 150x plus 9x squared. And bringing the x and the, so again, bringing the x and the y's to one side, I end up getting 16x squared plus 25y squared equals 400. And dividing through by 400, I therefore get that x squared on 25 plus y squared on 16 is equal to 1. And this represents the equation of an ellipse. So if I was to draw it for you, let's have a look. So across the x-axis it crosses at 5. Okay, so here it goes at 5, and on the y it crosses at 4. And that's pretty much the idea. So although that one was a lot harder and I couldn't immediately see what I was working with, by just plugging in z equals x plus iy and doing the algebra, I can now see that it looks like an ellipse. So that's our final example, and that more or less covers complex numbers. I think this video pretty much covers complex numbers in quite some depth. Pretty much covers everything you learn about complex numbers at the uni level. So this was a sample of our uni preparation course. If you'd like more info about our course, please head onto mathed.com.au, and yeah, thank you for watching.